my name is Anthony Sout, and this is Physics Lab 1, Objects Moving at a Constant Velocity. So in this lab, we're going to be capturing a video of an object in motion and use the program tracker to extract its position at any given time. Secondly, we're going to construct a computational model based on Newton's second law that shows a situation with zero net forces. And then at the end of the day, we're going to compare the tracker and the computational model to see how close our observed data is to having zero net forces. In the end, the slopes of the two models are nearly identical. Our R-squared value is 0.9976, which is very, very close to 1, and that indicates that the velocity remains constant over that time interval, meaning we have a net force of 0 working on that object. So a little bit of background here. What are these laws of motion that I'm mentioning? So Newton's first law states that an object in motion will stay in motion at the same speed and direction unless acted on by an outside force. This is the principle of inertia, and it's going to play a big role in what we're doing here. Newton's second law states that the acceleration is dependent on the net forces that are acting upon it. So here we have the velocity update formula, which is derived from Newton's second law. In this lab, we're going to be applying these laws in action. So the first law can be seen when the oats are rolling across the table. Newton's second law is in action in the code that models the oats. So why are we doing this? We're doing this because the human eye just cannot calculate each force individually that's acting on an object in motion. But we can use these laws to determine the net forces acting on the object. The main point of this slide is that if the slope of the computational model, where the net forces are manually set to 0, is the same as the observed model, that means that in reality, in the real world, there were no net forces acting on that object, and the velocity is constant. So here's our video that we based this on. Okay, here's some background into our tracker analysis. So this oats container is 10 centimeters or 0.1 meters, which was used as a reference point throughout the video, and the axes were placed at a 0-degree angle with the oats traveling in the negative x direction. This will have some implications on our results later. So up in the upper right-hand corner, you can see our graph of position versus time. That's a very linear graph. That's what we want to see. That helps us indicate right off the bat, this might be very close to 0 net forces. This video, a little bit of background, was trimmed to eliminate the initial acceleration, but as you can see, that's not a perfectly straight line. That's because the acceleration isn't exactly 0. And this is due to the minimal effect of friction and some human error with plotting the position in tracker. Here we have the initial velocity formula, which I used. On the next slide, that's going to be a little bit more important. This was used to help with the code. So here's the first section of my code in GlowScript. This helped me form the computational model. In line 32, you can see that I set the mass of the oats, and in lines 35 and 36, we have the initial position and initial velocity. I used the formula on the previous slide to calculate the initial velocity using the initial positions. On lines 39 and 40, you can see I set the time and the change in time. The change in time is based on the frame rate of my camera, which was 30 frames per second. On line 49, you have the end time, which is just limiting our code. Line 54 is very important. That shows that we have a 0 net force acting on this object in the code. Line 58 is the velocity update vector formula, and line 60 updates the ball's position. Here's our animation from that code. So a nice short little video there to just show what we coded. Here's our comparison of the two models, and this is where things get a little bit interesting. We have clearly a very, very linear match, right? So that R-squared value is very close to 1, and that's going to indicate that the slope of the computational model and the observed tracker data are almost the same. As we mentioned, this means 0 net force, constant velocity. And there's some errors in this, so I'm going to address that now by just saying it's likely due to taking the video at the wrong time and the effects of friction, which are negligible. All right, our results. While it's not possible to determine all of the individual forces acting on these oats, we can confidently say that the net forces are very near to 0 thanks to Newton's method. And some possible errors, other forces, are going to start acting upon the object once we get outside of this time frame that we analyzed. In conclusion, in this lab, I was able to apply Newton's first and second law to determine with some precision the net forces acting upon an object moving at a constant velocity. I was also able to determine that the object was moving at a constant velocity. Additionally, I used a computational and observed model to analyze these net forces. Thank you for watching my video, and I hope you learned about net forces.